Pythagorean theorem. And one of the many, many ways to prove the Pythagorean theorem is to look at a model like you see in number 1 that has a tray of figures on the left and a tray of figures on the right that have been rearranged, and using the areas of very common figures to prove the Pythagorean theorem. So if we take a look at the tray on the left. The tray on the left is made up of a large white square in the middle and then 4 triangles around the outside. So if we remind ourselves the area of a triangle, the area of a triangle is 1/2 the base times the height. Change colors here. And then the area of a square is equal to the side of the square to the 2nd power, side square. So we're going to use those formulas to find the area of each of these regions. So we're going to begin by finding the area of this triangle right here. So the area of this triangle is 1/2 the base times the height. And there are 4 of them that look just like that. There's another triangle here, another triangle here, and there's a 4th one here. So there are 4 of these areas, 4 of them. In addition, we have the area of this square on the inside. The area of the square is C times C, or C squared. So we have the area of the white region plus the area of the 4 shaded regions. So let's come down and simplify this expression. So that gives me C squared plus 1/2 of 4 is 2 times A times B. All right, let's go over to the right-hand side. And on the right-hand side, I have the same figures. You'll notice that I have the same exact figures in the left tray as in the right tray. They're just rearranged differently. And the first figure that I notice is I have the area of another square here. Another square gives me an area of A times A, or A squared. And then there's another white square right here that has dimensions of B times B, so that's B squared. And then we have 1, 2, 3, we have 4 triangles with the same dimensions as the triangles over here. And so we have 4, 1/2 base times height. So let's come down, and now we're going to simplify. What we see over here on the right, we have A squared plus B squared plus, and then 1/2 of 4. 1/2 of 4 is 2AB. And what we know is because the 2 trays are the same and they have the same area, we say that they are equal to each other. So the tray on the left is equal to the tray on the right. So as you can see, if we have 2AB on the left side of the equation and 2AB on the right side of the equation, we can cancel those, and that leaves me with C squared is equal to A squared plus B squared. So we've just proven the Pythagorean theorem by using the area of figures. There is, like I said, many ways to prove the Pythagorean theorem. And one of them, in number 4, is actually shown on this link. So I'm going to let you use this link on Khan Academy to see another way to prove the Pythagorean theorem. And we're going to use the Pythagorean theorem in number 6 to find the length of BC. So let's talk about what this figure is first of all. It is a 3-dimensional figure with, we have a plane, I'll call that the blue plane, that's horizontal, and then we have a green plane that's vertical. And what we notice is that there are two triangles. There's a triangle on the blue plane, and there's a triangle on the green plane. The triangle on the blue plane is a right triangle. So I'm going to redraw that right triangle over here on the right, and it looks something like this. Here's the right angle. And I'm going to transfer the values that I know from that triangle in the drawing. So we have point C, point B, and point D. And the distance from C to D, that length is 24. And the distance from B to D is 26. So because this is a right triangle, I can use the Pythagorean theorem to find the distance from C to B. So I'm going to use the equation a squared plus b squared equals c squared. So I just found the length from B to C to be equal to 10. So now what I'm going to do is I'm going to take the triangle on the green plane and I'm going to redraw that and we'll make it look like this. Now, here's what I don't know. I don't know if it is a right triangle. And that's what I'm trying to determine. Is triangle ABC a right triangle? So far I only know, well actually I know all three sides. Because I just found what BC is, I know what BC is right here, because I just found that length to be 10. Right? And I use this triangle over on the right to find the length of BC. So I have three sides in this triangle ABC. I have one side that's 6, I have another side that's 8, and I have a third side that's 10. And I need to arrange those three numbers in this triangle right here. So if I have the numbers 6, 8, and 10, I want to place them on the appropriate side. So the shortest side is 6, the longest side is 10, which means this side has to be the side that's 8. The question is this a right triangle? That's what we're trying to figure out. Is that a right triangle? So again, I'm going to use the converse of the Pythagorean theorem, which says if 6 squared plus 8 squared is exactly equal to 10 squared, then we're going to say yes, it is a right triangle. Or we're going to say no, it is not a right triangle. So 6 squared is 36, 8 squared is 64, 10 squared is 100, and 36 plus 64 does equal 100. So we're going to say yes, triangle ABC is a right triangle. And in number 8, I'm going to use the same converse of the Pythagorean theorem to determine if this is a right angle here. This is a right triangle. So using the converse, we're going to see if indeed 15 squared plus 36 squared is equal to 39 squared. I'm not sure, we'll put a little question mark here. Are they equal to each other? 14 squared plus 36 squared does equal 39 squared, we're going to say yes, it does form a right triangle. So here we have a diagram of a bridge that's made by many triangles, and what we know is all the triangles in this design are congruent. Sorry. And we have a length of the bridge is 48 feet, and the height is 15 feet. So if this entire length is 48, then we can take 48 and divide it by 3 to get the length of each of these triangles. And we know that they are the same because we know those triangles are congruent to each other, which means that these two sides are also 16 feet. And in number 10, it says what kind of triangles are they, acute, right, or obtuse triangles? And so we can definitely rule out obtuse triangles because there is no angle in the drawing that's greater than 90 degrees. And we can also rule out that there are no 90-degree angles in the drawing as well.